Hello. In this video, we're going to dive into a fascinating equation that describes one of the most fundamental processes in the universe, how heat travels from one place to another. By the end of our time together, you will be able to understand the core concepts behind the heat equation, identify its key components, and apply these concepts to simple scenarios. Our main goal today is the heat equation. It's a powerful tool used in physics, engineering, and many other fields to model everything from the cooling of a coffee cup to the transfer of heat through the Earth's crust. Think about the feeling of touching a hot stove. The heat is transferred from the stove to your hand. How can we describe this process mathematically? That's what the heat equation is for. Before we look at the equation itself, let's explore the physical ideas that it's built upon. Imagine a long, thin metal rod. If you heat one end of the rod, what happens? The heat doesn't stay at one end. It starts to spread to the colder parts of the rod. So heat moves from hotter regions to colder regions. This movement is called heat flow. The fundamental principle is that heat flows from hot to cold. Think about it. Your body loses heat to the colder air around you, which is why you feel cold and need a jacket. A hot cup of tea will cool down to the temperature of the room. This intuitive principle is the bedrock of the heat equation. Now, let's think about how quickly the temperature changes at a particular spot on the rod. How does the rate of temperature change relate to heat flow? If a lot of heat flows into a small section of the rod, its temperature will increase quickly. If heat is flowing out, the temperature will decrease. So there's a clear connection between heat flow and the change in temperature over time. To describe this mathematically, we'll use a function, U, that represents temperature. In our simple case, the temperature will depend on two things: the position along the rod, which we'll call x, and time at t. So we have a temperature function, U, that is a function of position x and time t. Now, let's talk about change. In calculus, the way we describe change is with a derivative. First, let's consider the change in temperature over time. We can write the partial derivative of U with respect to t. This term tells us how fast the temperature at a specific point on the rod is changing at a given moment. Now, let's think about how the temperature changes as you move along the rod from one point x to another. The partial derivative of U with respect to x tells us the slope of the temperature profile along the rod. It indicates if the temperature is increasing or decreasing as you move right. The heat equation will relate these two types of change. It will show how the rate of change of temperature at a point UT depends on the temperature profile around that point, UX. Okay, let's put these ideas together and introduce the heat equation. The equation connects the change of temperature over time to the curviness of the temperature profile in space. A measure of curviness is the second derivative. To use 2. The heat equation states that the rate of change of temperature over time is proportional to the second derivative of temperature with respect to position. Let's break this down. The left side, UT, is the rate at which the temperature is changing at a specific spot. The right side, 2 ya susu, x2, is the spatial second derivative. What does this second derivative tell us? A positive second derivative, 2u x2 0, means the temperature profile is concave up. It looks like a bowl. This suggests that the point in question is cooler than its surroundings. If heat flows from the surroundings to this point, its temperature will increase, meaning UT0. This matches the equation. A negative second derivative, 2u x2 0, means the temperature profile is concave down. It looks like a hill. This indicates the point is hotter than its neighbors. Heat will flow away, causing its temperature to decrease, meaning UT0. Again, this matches the equation. This proportionality constant, K, is called the thermal diffusivity. It's a material property that tells us how quickly heat spreads. Materials like metals have a large K, meaning heat diffuses quickly. Insulators like wood have a small k, meaning heat spreads slowly. So to recap, the heat equation is an elegant mathematical statement of our physical intuition. The temperature at a point changes over time because of the flow of heat, and the rate of that change depends on how the temperature is distributed in the surrounding space. Now, let's make this more concrete by looking at the simplest but most important solution, the steady-state solution. Steady state means that everything has stopped changing in time. The system has reached a perfect balance. If the temperature is at steady state, it's not changing with time. This means the time derivative, ut, must be 0. Let's substitute this into our heat equation. The left side becomes 0, leaving us with 0 equals k times the second derivative of u with respect to x. Since thermal diffusivity k is a positive number, this can only be true if the second derivative is 0. What kind of function has a second derivative of 0? If we integrate twice, we find that u of x is equal to a constant a times x, plus another constant b. This is the equation of a straight line. So, the steady-state solution to the heat equation is a linear temperature profile. What does this mean physically? It means that in a system that has settled down, the temperature decreases at a constant rate as you move along the rod. This creates a uniform heat flow, where the same amount of heat flows out of any section as flows in, keeping everything in balance. Let's apply this steady-state solution to a real example. Imagine we have a metal rod of length 1, with one end held at a hot temperature of 10 degrees and the other end at a cold temperature of 0 degrees. Our rod is 1 unit long. The boundary conditions are u of 0 equals 10 and u of 1 equals 0. Since the heat has stopped changing with time, the steady-state solution applies. We know the temperature profile must be linear. We use our general linear equation, u of x equals a times x plus b. Now we use our boundary conditions to find the constants a and b. First, let's use the condition at x equals 0. Substituting u equals 10 and x equals 0, we get 10 equals a times 0 plus b. This tells us that b must be 10. So our equation is now u of x equals x plus 10. Next, let's use the condition at x equals 1. We substitute u equals 0 and x equals 1 into our updated equation. This gives us 0 equals a times 1 plus 10. Solving for a, we find that a must be negative 10. Now we have our complete solution for the temperature at any point along the rod in steady state. The solution is u of x equals negative 10x plus 10. This equation describes the straight line that connects the temperature of 10 at x equals 0 to a temperature of 0 at x equals 1. This is a perfect example of a steady-state temperature distribution. Time for a quick check-in. Here's a question for you to think about. Imagine the same metal rod, but now instead of heat coming in from the end, there's a heater in the middle of the rod that continuously produces heat. So heat is generated at x equals 1/2 Feb. The ends are still held at 0 degrees. Think about our physical principle. Heat flows from hot to cold. If a point is generating heat, what must its temperature be compared to its surroundings? Will the temperature profile be a straight line or something else? Take a moment to consider. You can pause the video if you like. All right, let's think it through. If heat is being created at the midpoint, that point will be the hottest. Heat will then flow from the midpoint towards the colder ends. So the temperature must increase as you approach the center from either end. The steady-state temperature profile will look like an inverted bowl or a parabola. This kind of situation would require a more advanced version of the heat equation to solve. So far, we've focused on steady state. But what happens when things are changing? This is where the full heat equation really shines. Again, the equation is the rate of change in time equals k times the second spatial derivative. Solving this equation is much harder than the steady-state case. It describes how the temperature profile, use x, evolves over time. T. Let's think about this graphically. Imagine our rod is initially cold. At time t equals 0, we suddenly make the left end hot at 10 degrees. The temperature profile is a flat line at 0. Suddenly, the end is at 10 degrees. At this moment, the temperature curve is concave down near the hot end. The second derivative is negative. The heat equation says the time derivative should also be negative. Does that make sense? No. If the temperature is suddenly at 10, it's the hottest part of the rod. Heat should flow away from it, cooling it down. The temperature should decrease, and the equation holds. Ut is negative, which means the temperature decreases. This is correct. Over time, heat spreads down the rod. The point next to the end gets hotter, then the next point, and the next. The initial flat line starts to rise and curve. This process continues until, if you wait long enough, the temperature profile stops changing and becomes a straight line. Our steady-state solution. The heat equation elegantly governs this entire dynamic process. Let's test your understanding one more time. Here's a thought experiment. Imagine a very long rod, so long we can approximate it as infinitely long. It's initially at 0 degrees. At time t to 0, we heat up a single small spot at x of 0 to a high temperature, then we immediately remove the heat source. Here's the question. What will happen to the temperature profile in the rod as time passes? Take a moment to visualize it. How will the heat spread? Think about it like this. The heat wants to get away from the hot spot. Where can it go? It can only go left and right. Will it ever all disappear or just keep spreading thinner and thinner? Let's see. At time t0, we have a very sharp peak at x of 0 and 0 everywhere else. The heat at this peak will immediately start to diffuse to the cooler regions on either side. As time goes on, the peak will get lower and wider. The total amount of heat in the rod stays the same. It just spreads out over a larger area. The heat equation predicts that this heat will spread infinitely far, becoming infinitesimally small, but it never truly disappears. Let's quickly summarize what we've covered today. We started with the physical principle that heat flows from hot to cold, and that temperature changes over time in response to this flow. We then translated this into the heat equation, K2U x2, a partial differential equation that relates the rate of change of temperature to the curvature of the temperature profile. We solved the simplest case, the steady-state solution, which is a linear temperature profile. We saw how boundary conditions allow us to find a unique solution for a given problem. Finally, we explored the more dynamic, unsteady state behavior, seeing how the equation describes the diffusion of heat over time. The heat equation is a powerful and beautiful piece of mathematics that bridges the gap between our intuitive understanding of the world and a precise scientific description. I hope this introduction has given you a solid foundation for understanding this important concept. Thank you for watching.